This is Harsha Lakshmikant, a principal engineer at Juniper Networks, and I'm here to talk to you about how operators are on a journey progressing from telemetry to analytics to self-healing, and how, in the process, operators are able to have better visibility into the performance of their network, thereby running it more efficiently and optimizing performance. Let's look at the challenges that network operators are facing in the context of a modern car. Now, imagine that you're driving your car back home after a long day at work. This is, of course, in the pre COVID era when you could actually step outside your home. You don't really even think about, much less pay attention to the numerous systems, subsystems, and components that are there under the hood of your car and all around you, ensconcing you. The car is a complex piece of machinery with many different components and subsystems, many of which also run software. These components also generate large volumes of data. The car requires maintenance to keep it running smoothly. And as anyone who has experienced it firsthand can vouch, crashes are really, really bad. But as you're driving your car, all you care about is getting back home to your family, not really the internals of the car. And that's a good thing because it would be impossible to manually keep up with all the data that the car generates. Therefore, modern car vendors have created dashboards that abstract the data from the various components and where they are presented as actionable insights to the driver. If you're running low on fuel, you get an alert. If you're running low on engine oil, something lights up on your dashboard. If the engine battery is low, something pops up. Now think of your network. Like the modern car, switches, routers, firewalls, and data centers that you manage are again complex, have multiple subsystems and components, the control plane, the forwarding plane, kernel, host path, storage, which generate tons of data, which require maintenance to keep them running efficiently and smoothly. And as any operator can vouch, crashes are really, really bad. Notice the difference? Going back to the car analogy, most network operators are still managing the network using manual tools. Now imagine if you're managing not just one car, but a whole fleet of cars, which is what you're doing as a network operator when you're running a network providing end-to-end services to your customers. You have to worry about more things: device black hole detection, server connectivity, latency, forwarding plane consistency, and so on. The key thing is that we need to be able to abstract actionable insights to put you, the operator, in the driver's seat. Unfortunately, as of now, you're either in the firefighting crew dealing with escalations or the CSI crew trying to figure out what went wrong. Some of you who still remember walking across the room to change TV channels will also remember the effort required to check your old car's engine oil level. You had this dipstick that you would take out and wipe clean to make sure that it was grease free, which you would then insert into the oil tank and pull out to be able to see the current engine oil level. This is a polling approach which doesn't scale well. Guess what? This is exactly what we do with our legacy data collection tools such as SNMP and CLI. The process is manual and fetches limited data. As an example, some operators leverage CLI screen scraping to collect data, but this is fragile and prone to breakage and is likely to not work across vendors or even different versions of the same product. Ingesting syslog, which is basically unstructured, is problematic as well, since it doesn't help with automation. The mechanisms such as SNMP, CLI, and syslog that we have seen so far have limitations that restrict automation and scale. The use of the pull model does not scale well when what you want is access to real-time data. And if you try polling more aggressively, you could end up even causing the system to keel over due to the load that is being imposed on the system. Modern cars are not only about having a nice dashboard that provides you access to information of the components obtained by polling, they also have features that rely on timely, accurate data. For instance, a safety feature found on cars detects when the airbag gets deployed or the fuel pump gets deactivated, such as when a car suffers a sudden jolt against an object. The car then makes a direct call to emergency services, providing details of the car model, the time, and GPS coordinates. This requires access to real-time data. And as we journey towards a self-healing network, there's a need for operators as well to access real-time data from network devices. Modern telemetry approaches recognize the fact that there are different types of data collection. The first class requires a periodic update, think counters. The second class is event-driven, as in there's no point in keeping on broadcasting the state information if the state really hasn't changed. And finally, the third class is ad hoc, based on operator interest. For example, show OSPF neighbors. Streaming telemetry provides a push model to deliver data asynchronously, thereby eliminating polling. When a management station initiates a subscription request, it specifies the data of interest, the periodicity of updates, and the designated targets. This data is sent in a structured format. The higher granularity of data that is sent is comparable to tens of thousands of metrics per second, thereby allowing the operator to do things like performance monitoring. Streaming data to a performance management system enables network administrators to measure trends in node and link utilization and troubleshoot such issues as network congestion in real time. Additionally, streaming telemetry leverages a distributed architecture where the work is split across multiple components, the line card, the routing engine, and so on, thereby making it scalable. It's efficient, model driven, extensible, and is based on industry standards. And this makes it possible to have access to near real time data in vast quantities. Juniper supports this through native GPB, also known as Juniper Telemetry Interface or JTI, OpenConfig, and GNMI. Now let's take a quick look at what distinguishes these three types of telemetry. It basically boils down to what API spec, what data model, what encoding, and what transport get used. The rightmost column represents GNMI, which uses the GNMI RPC as its API, OpenConfig for its data model, GPB GNMI for encoding, and gRPC for transport. The one to its left, the middle column, represents OpenConfig, and the very first column represents JTI. Now, how do you decide what to use when? From an encoding perspective, if you're looking for a format that is self-describing, which means that your collector doesn't have to have a key to understand the telemetry syntax, then you could use OpenConfig or GNMI. But if what you're looking for is efficiency on the wire, then native GPB is 2 to 3 times more efficient. Dial out or dial in could be another consideration. With dial in, the devices wait for the initial subscription request coming from the client. But if you're behind a firewall, this might involve opening up ports. With dial out, the device initiates the connection to the client. JTI supports only dial out, while GNMI supports only dial in. OpenConfig supports both dial out and dial in. Encryption could be another consideration. gRPC comes with SSL authentication and encryption, which is available in both OpenConfig and GNMI. Now that streaming telemetry provides us access to copious amounts of real-time data, we need to be able to leverage this big data and put it to use. And the challenge now becomes figuring out what to do with all of this data. And this can be achieved through AI insights. While that may sound as a daunting task to many of you, Kirti Kompella, the CTO of engineering at Juniper, refers to augmentation as a good first step. This is achieved by augmenting existing NOC processes with ML algorithms, providing insights for the operators to run networks more efficiently. In the context of a security breach that generates a large number of messages, say 10K messages, one could handle them manually using human intuition and expertise to determine which ones to prioritize, or have a machine analyze and prioritize them for you and present a human with the top 5 threats to dispatch, or build a machine that is fully capable of prioritizing them and taking the right actions for each. While it would be great to have a machine do all the stuff for you, having a machine prioritize and give you actionable inputs would be a considerable improvement over chasing down things manually, which is where most network operators are today. And the good news is that this revolution has already begun. Now, when we think about this augmentation that Kiriti talks about, we tend to find that customers fall into 4 primary categories depending upon their pattern of telemetry consumption and deriving analytics insights. The first category is customer persona A and refers to an organization who has a large in-house team to do the data mining, where all they really need is access to big data. This is something that we've already covered as part of streaming telemetry. They understand ML and AI and want to do things themselves. The second category, customer persona B, refers to an organization that already has a data lake and needs the devices to beam data out in their specific format of data model, encoding, transport. We have a solution for that through which the device beams out data in the required format. The third category, customer persona C, refers to an organization that wants to leverage open source collectors to consume telemetry. We cater to those customers as well through open sourced Juniper plugins for some of the well-known collectors. And finally, we get to the fourth category, customer persona D, who needs a complete solution for solving his business problems. While this category certainly understands the benefits of streaming telemetry and ML, they aren't sure about where to begin and require the vendor to provide them a complete solution. We have a solution for that as well, Healthbot. Now, considering these four personas, I'd like to take a minute to focus on personas B and C. While Juniper devices already stream data as JTI or OpenConfig or GNMI, where what differs is the data model, encoding, and transport, some customers, persona B, might already have a data lake or collector where they want the data to be beamed in a specific format. And to that end, we have Network Telemetry Agent, NTF agent, that sits on the device and which is written as a plugin architecture capable of changing the encoding, data model, and transport. The southbound to NTF agent is always OpenConfig over gRPC, but the northbound plugin can convert this to any other format. For example, the output from NTF agent could be Avro encoding published on a Kafka bus. These plugins can be developed by customers themselves or by engaging with professional services. For the open source collector enthusiasts, Persona C, we support the latest and greatest flavor of the season, such as Telegraph, Fluentd, or Logstash, by developing and contributing southbound plugins to these open source projects. This in turn enables the open source collector that you've downloaded and configured to start collecting streaming telemetry data from Juniper devices right off the bat. Incidentally, given that these open source collectors are implemented in different languages, contributions to these projects have spanned across Go, JRuby, and Ruby. I'd like to spend the rest of this session talking about customer persona D, where while the premise of telemetry is interesting to the customer, what really matters to the customer is that it solves his or her business problems. Enter Healthbot, which is an analytics app that is like a doctor for network devices and services. It leverages ML algorithms to provide insights and observability and allows for proactive diagnosis, health monitoring, and root cause driven closed loop remediation. But Healthbot is not just a visualization and monitoring tool. It's also a platform which is open and programmable and designed with a microservices based scale out architecture. So now, rather than having to worry about and keep track of the different components individually, you get an abstracted, actionable view of your devices and services, thereby literally putting you back on the driver's seat. Healthbot as a platform is broken into four key capabilities: the collector, the data filter, analytics engine, and notification engine. Healthbot achieves this by collecting the data. To that end, it supports multiple ingest mechanisms, right from modern streaming telemetry, falling back to legacy methods where telemetry isn't supported, and also spanning custom ingests where it can pick up data from a customer's existing data lake. Now that all this data has been obtained, it's necessary to filter it out before you can make sense of it. For instance, subscribing to slash interfaces in OpenConfig results in 70 plus metrics being streamed out, while the fields of interest might be restricted to only 4 octets and error counters for both TX and RX. Healthbot filters out the unnecessary 66 metrics, thereby reducing the noise. Similarly, if what matters to the operator is just monitoring XE interfaces, Healthbot can be programmed to filter out all the other rows corresponding to FE and GE interfaces. And no matter which ingest channel the data is obtained from, Healthbot normalizes the data. Similarly, aggregation allows the collection of large volumes of traffic flows and have it aggregated over time, say a period of 1 minute before processing it, thereby increasing efficiency. Tagging allows for making apples to apples comparisons at a later point of time. For example, comparing the traffic patterns of a football match that is occurring this weekend versus those that occurred in the past. This filtered, tagged, aggregated, and normalized data then gets acted upon. This is done through two ways: in the form of domain expertise, which is in turn augmented by ML algorithms to generate insights on the health of the various devices, components, and network services. These insights are then delivered on the GUI dashboard as notifications on a Slack channel or in Microsoft Teams. As I had mentioned, Healthbot leverages ML algorithms to provide insights. Let us double click on this. There are 4 vectors here. From a time perspective, anomaly detection uses historical behavior of each device to bucketize and detect anomalies or deviations. Is the current CPU utilization an anomaly compared to the same time last week? Outlier detection works with respect to a peer group. When a bunch of devices are performing the same function, you could check whether the parameters of a device, such as the number of broadband edge subscribers, is out of range compared to the operational range of the other devices. Cross-correlation helps you identify where your resources are being consumed. Is an increase in memory correlated to an increase in prefixes installed or firewall filter terms? And finally, prediction allows you to forecast future values based on historical data to identify conditions such as link saturation, allowing you to do preventive maintenance or do a make before break rather than waiting for disaster to strike. At the heart of Healthbot are playbooks, which happen to be the operator input to Healthbot. There is a rich library of playbooks developed by TAC, engineering, the field, and even customers that are open sourced and available on GitHub. A set of curated playbooks also ship with each version of Healthbot as part of the factory default playbooks that come pre-installed in the app. These contain data on what to collect, sensors, what to process, say converting instantaneous data of CPU utilization into something more interesting like a 5-minute running average, evaluation of the condition of health, either based on static thresholds or by using ML techniques, and finally triggering an action along with posting results. These results can be consumed in different forms through health views, through alarms raised, getting reports, visualizing the data. These results can also be used to derive different outcomes such as external notifications and posting to webhooks. Going back to our car analogy, as the automotive industry journeys towards self-driving cars, their goal isn't just to process data and alert the driver through a dashboard anymore. The car now senses when a vehicle in front of it has suddenly slowed down or shifted lanes, and it automatically brakes on behalf of the driver. This process leverages real-time data to not only generate insights, but also to take action. Going back to the example that we saw about 10K messages regarding a potential security breach, what if we could have the machine take action directly in addition to notifying the operator? Healthbot does this for you today. It can take closed loop action when a health KPI is read, and that includes taking a user defined action such as rebooting the box or informing a controller such as Northstar, which uses a path computation engine and PCEP to put an unhealthy node in maintenance mode and having it recompute the LSPs, thereby avoiding that node, or initiating a workflow involving approval based action, or raising a JTAG ticket for RMA, or opening an incident on ServiceNow. To summarize, Healthbot is not just an analytics app, but also a platform that generates insights on the health of your network and that is capable of taking closed loop action. Healthbot enables you to collect and visualize data by defining customizable KPIs, which help you to filter out and visualize this information from the broader data lake in such a way that results in actionable insights regarding the network device and service health. Healthbot's ML algorithms can be used to help network operators detect, assess, and respond to anomalies. Its machine learning algorithms can also be used to predict trends and forecast future values or status of network devices or systems. Using its data analysis capabilities, Healthbot is able to identify the root cause of an issue and figure out what went wrong when a KPI becomes red. Healthbot's algorithms can also analyze log files and filter out noise to emphasize data that matters most to network operators. Healthbot triggers can be used to drive specific actions, providing a closed feedback automation solution. No matter where you are on this journey of the telemetry and analytics story, Juniper has you covered. Whether you're a do-it-yourselfer, whether you're somebody who already has the tools and just wants the vendor to integrate, whether you want to go down the open source collector path, or whether you're looking for an end-to-end solution to solve your business problems. And if you're looking for a complete solution, Healthbot provides you insights on the health of your devices and network services by leveraging ML algorithms, intelligently automates the diagnostic workflow, and sustains your overall performance goals. And that concludes this session. Thank you for attending and enjoy the rest of the summit.